and welcome back to another video on energy changes. So in the first video we looked at what endothermic and exothermic means, that some reactions absorb more energy than they've released, or others release more energy than they absorb, and we can represent it by using two different graphs representing the amount of energy that they start with, the amount of energy that they end with. And that kind of gives us the difference between endo and exothermic reactions. So today we have we looked at enthalpy. We introduced the word enthalpy and the delta H, the sign that we use, or the symbol that we use for enthalpy is the delta H, the change in energy. And there's different ways of working out the amount of energy that is either absorbed or released in the reaction. And today is kind of like leading into that first way that we can work out the amount of enthalpy change, or the amount of energy change, and that is by looking at bonds that are broken or made. And remember, we said when the reaction happens, the two molecules or the reactants that we have need to break their bonds initially. So if you think of building Lego, if we have an existing little structure, we need to break those bonds first before we can rebuild them into a new substance or a new product. So that's exactly what happens in chemistry and real life as well. So we've got our atoms that needs to break and so that they can reshuffle and remake a new substance. And that amount of energy that is needed to break those bonds can be calculated, or chemists have calculated it for us. So we just use the values that we know exist, and then with the reshuffling, we know the values that the amount of energy released when those bonds are made. So we're just going to use that and do some maths and find out what the enthalpy change or energy change is for that reaction. Okay, so before we do that, we just need to understand that all substances undergo these changes or reshuffling and reactions, but not just in chemical reactions. We can look at physical reactions as well. So physical reactions are reactions where atoms, the same atoms, they don't reshuffle, they just go into different states. Or they look a bit different, but they're exactly the same chemical elements that they started with. And an example of that is when water freezes or water evaporates and becomes a gas. So we can look at that graph again, or we can represent that as a graph. So at the start, we look at ice. Ice is a certain amount of energy, right? So we look at that as a solid. And then what happens is we give it, okay, so we'll start with that one. And then we'll start giving ice energy. So if we take a block of ice on and put it on the bench in the kitchen, what happens is it doesn't really quickly start melting. It'll stay an ice block for a little while. And what happens there is, as it stays in ice block, it's still absorbing energy from the environment. So from your kitchen and the house, all the energy is going into the solid, into the ice block. You can't see it melting yet, but it's still, all that energy is going in. And what it does is, because with a solid, all the particles are close together, they are being held with intermolecular forces. And we remember we talked about the solid, the covalent solids, or the molecular solids. So these ones are the molecular solids with weak intermolecular forces, and those forces need to be broken with the amount of energy for it to actually start like separating and becoming a liquid. So this is the time where it absorbs energy, and all those bonds between the molecules of the atoms are being broken, and then suddenly they reach a certain point when that solid isn't a solid anymore. All those bonds are broken, and now it is a liquid. Okay, and it's a happy liquid. It's just there. And then we could decide we want to give this liquid a bit more energy. So again, it'll stay liquid, it absorbs energy. And again, those bonds between the liquid and the particles start breaking, being absorbed up to a certain point, and then it becomes a gas. Okay, so we need to identify this part as the latent part. And what happens in this part is it's busy absorbing energy to break those bonds, but it's not yet changing state. Okay, so that's where the energy absorption takes place between these molecules or these phases of state, there's energy being absorbed, but we can't see it. And the temperature, it doesn't change of the solid or the liquid or the gas yet, because it's just kind of like taking all that energy to absorb and break those bonds. Right, so this is what happens when we look at solid to a liquid. We need to add energy. From a liquid to a gas, add energy. When we have a gas, all these particles, remember bonds, so these bonds are broken. In order to break bonds, you need energy to break those bonds. So now this gas has heaps of energy. It's moving around. Gas particles have quite a high amount of energy, and that's why they're moving and vibrating quite quickly. And then suddenly, we want them to turn into a liquid. So what we need to do is we need to remove some of this energy from the gas in order for it to kind of settle down and become a liquid a little bit more. And what happens then is we need to take the energy away. Okay, and when we take the energy away, it'll get released. So it's an exothermic reaction when it goes from a gas to a liquid and from a liquid to a solid, because it releases all that excess, all that extra energy it used to have to go into a lower state of energy. Okay, so going down this way is an exothermic reaction. When we go up this way, it's an endothermic reaction, because they need energy for those bonds to break. Okay, so we've looked at the energy changes on the graph, or the phase changes, and we know that if it goes from a liquid to a solid to a liquid to a gas, we need to add energy to it to break those bonds. When it goes from the opposite, from the gas to the liquid to the solid, it gives off energy, it releases energy. Okay, and that balance between the energy released and absorbed, that will tell us the enthalpy, the total change in energy in this whole reaction. Okay, so the first way we can calculate it is by using the amount of energy that we know that is required to either break or make these bonds. Okay, so they'll give you a table like this that's with existing numbers, with existing energy values. So we know to break an HH bond, so if it's like H2 that has a bond between them, if we need to break that bond between the H's, it requires 435 kilojoules of energy. Okay, so or kilojoules per mole of energy. If we want to make an H2 molecule, if we want to take two H's and squash them together, we will release 435 kilojoules per mole of energy. So this amount of energy is kind of like universal for either breaking or making bonds. And then we can use this and add up how many bonds have been broken and how many bonds have been made. And then we do a little bit of maths, and we can find out what is the total difference in the amount of energy in that system. Okay, so for example, this is called, we're using our bond enthalpy. We're using the amount of energy needed that we know about making and breaking bonds, and we're calculating the amount of enthalpy, the amount of energy change in this whole reaction. Okay, so let's have a look at the first example that they'll give us. We've got an H2, and we need to, we'll put it up there so you can see. H2, and we're adding it to Cl2, and then we are going to make two HCl's. Okay, so we've got two of these atoms or reactants are going to need to be broken up, and when they've already broken up, what we're going to do is we're going to reshuffle them and then make two molecules of HCl's. Okay, so the first step is to identify how many bonds have been broken. So let's have a look at this one. The first one, we've got H2, so it means that it's like two little H's that's next to each other. So there's one bond between them. So we know we've got an HH bond on this side. And then we have Cl2, so that's also two atoms of Cl that's bonded together, and we know we've got a Cl bond. That's there as well. So that is that needs to be broken. And then when we look at what is made, we've got an H and a Cl, but we've got two of them. So we've got, so if we have an H and a Cl molecule, we have another H and a Cl molecule. Colour these ones black. There you go. So we've got two HCl molecules. So we've got two bonds of HCl's. Okay, and those two, so let's have a look. Now we're going to add some values. So the amount of energy needed to break this HH bond is 435. 435. And we're going to add the Cl, the amount of Cl needed for the Cl's is 243. So 243. We add that up. That's 8, 7, 6. Okay, so that's the total of energy needed to break this side of all these bonds on the side of the equation, okay, or this reaction. When we look at this one, an HCl bond is 433, but there's two of them, so we're going to multiply it by 2, 431, sorry, and that is going to be 862. Right. You can't see that. So 862. So now that we've got these two numbers, we have the amount needed to break them. Broken. Is 678. And the amount needed to make these bonds is 862. Okay, and now let's get rid of all this. What we're going to do is we are just going to use the reaction or the equation delta H equals bonds broken minus made. So when we look at that, let me just get my calculator. Broken is going to be 678 minus 862 minus 862. And that will give you minus 184 kilojoules per mole. And when we look at this 184 minus or negative 184, what does it tell us about this type of reaction? So we know that when it's a negative number, it means that more energy is released than what they started with. Okay, so when we looked at the H2 and the Cl2, they would have had a certain amount of energy needed to break those bonds, but more energy is released than what was needed to break them. And because more energy is released, we know that's an exothermic reaction. So let's quickly go through it again. They give you a table of energy requirements needed to either make or break the bonds. So that's universal, and it doesn't have a sign because it could go positive or negative depending on what I guess what the reaction is. Then what you do is you look at what atoms we have to start with, identify the bonds between them that we need to break, and then find out what we've made and identify the bonds that we had to make, add the values to it, and then pop it into this equation. Delta H equals the bonds broken minus the bonds made. Pop it in, and then that will tell you whether it's an exo or endothermic reaction based on the sign. So if it's negative, we know it's an exo, or if it's positive, we know it's an endothermic reaction. Chemistry, baby, you and me.